So, in the last lecture we were discussing the distinction between a laminar flow and a turbulent flow in a pipe. And I told you that for Reynolds number less than about 2100 or so, the flow is laminar, the velocity profile is parabolic, and the cross stream transport takes place due to molecular diffusion. When the Reynolds number exceeds about 2100, the flow transitions to a turbulent flow, and the turbulent flow is characterized by a more plug like velocity profile with a smaller curvature at the center, sharper gradients at the wall. The velocity gradient at the wall is sharper, it is higher than what it is for a laminar flow. There are fluctuations in all three directions in a turbulent flow, large fluctuations comparable to the mean velocity, and it is these fluctuations in correlated parcels of fluid in correlated motion called eddies. These are what transport mass, momentum and energy across the flow, in contrast to molecular diffusion for a laminar flow. And because of this mechanism, because this mechanism is far more efficient than that molecular diffusion mechanism in a laminar flow, therefore, the transport rates are much higher in a turbulent flow in comparison to a laminar flow. The velocity fluctuations, there are fluctuations in all three directions about this mean velocity. Okay. This transition happens at, so I will just go through some of the features of a turbulent flow. Okay. This is primarily at high Reynolds numbers. Okay. There is a transition from laminar to turbulent flow. At low Reynolds number, when the inertial effects are not important and the viscous effects are dominant, the flow is always laminar. At high Reynolds number, when the inertial effects are dominant, there is a transition to a turbulent flow. That transition could be an abrupt transition like you have in a pipe flow, for example. It could be a more gradual transition like the wake in the flow behind a particle, for example. In all cases, the transition takes place at when the Reynolds number exceeds some value, and turbulence is a high Reynolds number phenomenon. Okay. And turbulence is characterized by large fluctuations. Okay. Okay. At a given location, as a function of time, if you measure the velocity as I had shown over here, you will find that the velocity fluctuates about its mean value, and the amplitude of the fluctuations could be comparable to the mean velocity itself, okay, when the Reynolds number becomes very large. So, the flow is characterized by large fluctuations in all three directions. Okay. Another characteristic of turbulent flows is that it is necessarily what is called three dimensional. In the flow through a pipe, for example, the mean velocity is in the axial direction along the pipe. However, the fluctuating velocities are in all three directions. There is no such thing as a two-dimensional turbulent flow, because the velocity fluctuations are necessarily in all three directions. Okay. Therefore, turbulent flows are always three-dimensional. Okay. They are what are called highly diffusive. Dispersive is a more proper terminology for this, because it is not molecular diffusion, it is actually dispersion due to the fluid velocity fluctuations. That is a convective transport due to the fluid velocity fluctuations, due to correlated parcels called parcels for fluid in correlated motion called eddies. These are temporary. Okay. They form and then they break up. The correlations form for some period of time and then they break up. That period of time is what is called the eddy turnover time that I had talked about last time. Okay. The time period for which a parcel of fluid of a certain scale is in correlated motion. Okay. And they are also, because they are diffusive, they are also highly dissipative. Okay. Recall that dissipation takes place due to the viscous effects, fluid friction, the strain rate in the fluid. And in one of our earlier lectures, I had told you that the rate of dissipation of energy per unit volume is equal to the viscosity times dVx by dz the whole square for a unidirectional flow. Okay, this is only for a unidirectional flow. It is more complicated for 3-dimensional flows. Nevertheless, this dissipation takes place due to the fluid strain rate, okay, the straining that takes place in the fluid. In a laminar flow, the velocity is the average velocity of the pipe, for example. The characteristic velocity will be the average velocity. Okay, so, if I wanted to estimate what is the diffusion rate of dissipation of energy, the per unit volume in this case, the average velocity is the characteristic velocity and the average diameter is the characteristic length scale. Okay. So, this is what you would estimate for the rate of dissipation of energy in a laminar flow, okay, per unit volume. Turns out in a turbulent flow, because of the velocity fluctuations, the rate of dissipation of energy is actually much larger than this estimate. We will come back and we will estimate this. Okay. It turns out that the rate of dissipation of energy is much larger than this estimate. That is because it is not the mean velocity which varies over the pipe diameter that is the dominant contribution to the dissipation rate, but rather the fluctuating velocities within the eddies which vary over a length scale comparable to the eddy size. It is those velocities that actually result in the dominant contribution to the dissipation. Okay. Therefore, it is highly dissipative. And two further properties. Okay. One is that it is a continuum. Okay. It is a continuum phenomenon. Okay. The smallest scales in a turbulent flow are always much larger than the molecular scale. If you recall, I had told you that the turbulent flow contains eddies of a range of sizes. Okay. It contains eddies of a range of sizes. The smallest of these is always much larger than the molecular scale. Therefore, it is a continuum phenomenon. It can be described by the same equations that are used to describe a laminar flow. Okay. And turbulence is what is called a flow property. Okay. What that means is that, for example, diffusion in a laminar flow is a molecular phenomenon. Okay. It depends upon the root mean square velocity and the mean free path of the molecules in the liquid or in the fluid. Okay. It depends upon the molecular microscopic molecular length scale and the molecular velocity scale. In a turbulent flow, transport depends upon the length and velocity scale of the turbulent eddies. So, it is a flow property. Okay. It is not a fluid property. Okay. So, these are some of the properties of a turbulent flow. Okay. Why does this transition to turbulence take place? Okay. So, first thing is, as I said, turbulence is a continuum phenomenon. Okay. The equations for a turbulent flow are the same as those for a laminar flow. you can solve the same equations to get both the turbulent and the laminar solutions. By same equations, I do not mean the simplified equations for a steady laminar flow for a unidirectional flow. Okay. If you recall that I had got the solutions for, I had simplified the equations for a laminar flow as 0 is equal to minus dP by dx plus mu by r those were for a steady flow. A turbulent flow is not steady, and therefore, you do have the inertial terms in the equations for a turbulent flow. Okay. What we call the Navier-Stokes equations, which contains both the inertial terms and the viscous terms. If you recall, when we did the derivation, when we did this derivation, I had told you that the momentum entering a differential volume and the momentum leaving a differential volume is the same, because the velocity is independent of position. That is not true for a turbulent flow, because the velocity on both surfaces fluctuates in space and time, and therefore, you have to include both the inertial and the viscous and the pressure terms in the conservation equations. Those equations turn out to be equations for the vector velocity field. Okay. Note, for the turbulent flow, the velocity is not in one direction. The flow on average is in one direction, but the actual velocity is instantaneously fluctuating in all three directions and in time. Okay. So, not these equations, okay, but rather the equations for the vector velocity field, which includes the inertial and the viscous terms. Those are the same for a laminar and the turbulent flow. Therefore, both laminar and turbulent flows are described by the same equations. The complete Navier-Stokes equations for the vector velocity field containing both inertial and viscous and pressure terms, the derivation of which is beyond the scope of this course. So, it is described by the same continuum equations. Okay. The turbulent and the laminar flows are described by the same continuum equations. That implies that there are multiple solutions for the same pressure gradient and for the same boundary conditions for these continuum equations. Okay. The solution of the equation, okay, there could exist more than one solution of the equation. One of those solutions is what is called a laminar flow with straight streamlines, parabolic velocity profile. The other solution is what is called a turbulent flow. And an equation can have multiple solutions only if it is what is called nonlinear. Okay. A linear equation is one where the field variable appears to the first power in the entire equation, okay. Or you have inhomogeneous terms as well. All of the equations that we have been studying so far are linear equations, and for linear equations, if the boundary conditions are properly specified, there is a guarantee that there exists only one solution, and that is unique. For nonlinear equations, there is no guarantee. Okay. Now, the fluid equations contain inertial and viscous terms and the body forces, the pressure gradient, etc. The viscous terms are always linear. Okay. For a Newtonian fluid, the viscous terms are always linear. The inertial terms are not, and the reason the inertial terms are not linear is because the quantity being transported, the momentum, is the same as the quantity that is doing the transport. Convection. Convection is due to the velocity field. What is being transported is the momentum, which is also proportional to the velocity field. So, the quantity being transported and the mechanism of transport for the convective terms in the momentum equation are the same. And because you are multiplying two terms which depend upon the velocity, the Navier-Stokes equations are nonlinear in the velocity field. Okay. Specifically, the inertial part of the Navier-Stokes equations is nonlinear in the velocity field. It is a nonlinear function of the velocity field. For that reason, the equation is nonlinear when the inertial terms are included. If the inertial terms are neglected, as is done at low Reynolds number, the equations are linear, the solution is unique, and there is only one solution, the laminar solution. At high Reynolds number, the inertial terms are nonlinear, and because of that you could have multiple solutions. One of those solutions is the laminar flow and another solution is the turbulent flow, okay, in this case. So, it is because of this nonlinear term that you have multiple solutions, one is laminar and the other is turbulent. And then the question arises, which of these solutions is selected, okay, which of these solutions is selected in an actual flow field. You have multiple solutions. So, obviously, in a realization you can see only one solution. For example, for Reynolds number less than 2100, you see only one solution, which is the laminar solution. When it exceeds 2100, you see only one solution, which is the turbulent solution. How are these solutions selected? Okay. And that has to do with what is called the stability of the equations, the stability of the solutions. Okay. So, I will use an oversimplified analogy to illustrate what is the meaning of stability. Okay. So, if I have, okay, in a valley, okay, an object, okay, this object is in equilibrium because when it is at the bottom, okay, let us say I had a gravitational field, okay, an object in a gravitational field at equilibrium at the bottom where the slope is equal to 0, okay, the minimum. Okay. That is because the forces are all balanced, okay, and it is stable. Okay. So, I have an equilibrium state here. I have an equilibrium state, okay, where the forces are all balanced. The force exerted by the object on the bottom is in the downward direction along the direction of gravity, and that is exactly equal to the reaction, okay, of the bottom of the bottom surface. Now, if I had, for example, the same thing, but rather the surface curved the other way, okay. Okay, if I had the surface curved the other way, this is also at equilibrium. The forces are exactly balanced. When it is sitting right on top, the forces are exactly balanced. Okay, the forces are exactly balanced. The difference is that in this case, this is a stable equilibrium. Okay. So, if I displace it a little bit to the right or the left, this object will return it to its original state. Okay. Whereas, this is an unstable equilibrium. Okay. It is an unstable equilibrium. If I displace it a little bit to the left or the right, it will go to some other state. It will not return to its original state. Okay. So, that is the distinction between stable equilibrium and unstable equilibrium for a simple one dimensional system. And you have another state which is called a neutral equilibrium. Okay. Okay. If you displace this object, it stays at the displaced location. Okay. So, it is a neutral equilibrium. Okay. Okay. So, the equilibrium is related to the balance between forces in that state. Okay. The stability or instability is related to the disturbances around that state. Okay. So, that is the distinction. Now, as I said, this is a simplistic analogy. Okay. This is just a one dimensional problem. Okay. In a pipe, for example, the velocity is defined at each point in the flow, and at each point there are three components of the velocity. Okay. In general, the velocity is defined at each point in the flow, and at each point there are three components of the velocity. So, this is what is called a high dimensional system. Okay. But the same principle applies there. Okay. The laminar flow is a solution of the equations. Okay. It is a solution in the sense that this equilibrium is a solution. Okay. So, this I had shown you the analogy for an object in a valley or an object on top of a hill. It is sort of similar for example, for potentials, okay, for an object in a potential, for example. Okay. It will go to the location of the minimum of that potential. Okay. And there are other analogies that one can think about. As I said, in a pipe flow, the velocity is specified at each location in the pipe, and the velocity can be in 3 directions at each of those locations in the pipe. Okay. And so, one can place a disturbance, a small disturbance at any location in any direction, okay, in this pipe flow. Okay. So, it is a high dimensional system. Okay. There are other configurations also where stability becomes important. Okay. For example, if we had done this before, we had okay, 2 co-rotating cylinders. Okay. Moving with 2 different velocities, angular velocities. Omega I is the inner cylinder, omega O and omega I. Okay. With 2 different radii, RO and RI. Okay. Okay. And in this flow, you will have a laminar flow when the ratio of the inner and outer angular velocities is below a critical value. When it exceeds a critical value, there is a spontaneous formation of what are called convection rolls, okay, in this. Okay. There is spontaneous formation of what are called convection rolls in this particular flow. Okay. And this transition takes place when the relevant dimensionless group exceeds a critical value. Okay. This goes by the name of Taylor-Couette flow. Okay. When the transition, this transition occurs when this takes place when the ratio of inner and outer cylinder velocities, angular velocities, exceeds a critical value. Below that, you will have nice circular streamlines going all the way around the axis. At some point, this will break up into smaller structures, okay, which are called convection rolls, okay, which are called convection rolls. This is also observed, for example, if you have a fluid layer heated from below. Okay. The temperature profile, if I am heating it from below, okay, I am supplying heat from below, the temperature is a decreasing function of height. Okay. The temperature decreases with height because I am heating it from below. Okay. And when it is heated from below, the fluid on top is colder and has a higher density. The fluid below is hotter and has a lower density. And so, you have an unstable stratification where you have a higher density fluid sitting on top of a lower density fluid. And here also, when the Rayleigh number, okay, we had seen that in the context of natural convection, when this exceeds a critical value, you get the formation, the spontaneous formation of rolls. Okay. So, these are examples where the laminar flow becomes unstable, okay, because of different mechanisms and automatically forms more complex structures. And if you further increase the dimensionless groups, these will ultimately go to a turbulent flow. Okay. So, you get this gradual, okay, progression to a turbulent flow starting with the formation of regular structures. Okay. In both of these cases, the mechanism of instability is this one. Okay. The flow that is stable at a particular value of the parameter becomes unstable. Okay. So, that is the progression for these kinds of flows. This thing is called the Rayleigh-Bernard. Okay. So, why did I go through this detour to tell you about these other different kinds of flows? It is because the case for a pipe flow is different from these two. Okay. Case for a pipe flow does not correspond to either of these cases. In the case of a pipe, you do not have this kind of a transition. In the case of a pipe, you do not have this kind of a transition from a stable to an unstable state. Okay. What happens in a pipe flow is this. If you look at the stability of the laminar flow, the landscape that I had drawn for you, this is for the stable state. Okay, this is stable. Okay. This never transitions into an unstable state of this kind. Okay. No matter how high the Reynolds number is, it never transitions to an unstable state of this kind. Okay. Okay. I am drawing it schematically, of course, one should not take this literally, okay, but it never transitions to this state. Okay. What it does transition to, okay, is something that looks like this. Okay, something that looks like this. Okay. What it means is that the laminar flow is stable for all Reynolds numbers. Okay. The laminar flow continues to be stable for all Reynolds numbers. However, this is unstable to finite amplitude perturbations. In other words, if I increase the disturbance beyond a certain value, okay, this will go to some other state. Okay. If the disturbance is infinitesimal, okay, it is going to remain in that state. It never goes to an unstable state. So, this is an unstable state. This is unstable to infinitesimal. Okay. This is unstable to finite amplitude. So, in a pipe flow, the system never goes unstable to infinitesimal disturbances, it goes unstable to what are called finite amplitude disturbances. And in fact, currently there is no calculation that shows that there is an instability for the fully developed laminar flow in a pipe. There is the flow does become unstable to finite amplitude disturbances. So, you need some minimum level of disturbances for the flow to become unstable. And this has been verified in experiments that if you take care to ensure that there are no disturbances in the system, the flow can be maintained in the laminar state for Reynolds numbers as large as 100,000, for example. Okay. If care is taken to remove all disturbances both at the inlet of the pipe as well as in the environment. However, in real situations there are always disturbances, and because there exist these disturbances, the flow in a pipe transitions to a turbulent flow at a Reynolds number of approximately 2100. Okay. It could be more or less, okay, depending upon the level of disturbances, for example. Okay. I should caution here that this is still an active area of research. We still do not understand this transition. Okay. What we do understand so far is what I have told you here, that the system in a pipe is qualitatively different from all of those other instabilities that we see in nature, such as rotating fluids and heated fluids. In those cases, the system does in fact become unstable, and you can show theoretically that the system has become unstable. In the case of a pipe flow, theoretically it is known that there is no transition to there is no instability due to infinitesimal disturbances of the kind that is shown over here. Okay. Any instability that exists is due to finite amplitude disturbances of the kind shown here. Okay. And this is what causes the transition from a laminar to turbulent flow in a pipe. Okay. And this is the mechanism which is still not fully understood, but it has significant consequences for us because, as I had explained, the characteristics of laminar and turbulent flows are very different. So, what is the characteristic of a turbulent flow? I will continue that in the next lecture. First, the characteristics for turbulent flows themselves, and then some description of the characteristics for a turbulent flow in a pipe, okay, where you have a wall where the velocity fluctuations have to decrease to 0. I will continue this in the next lecture. I will see you then.